Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 50+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to unlock AI's potential to serve humanity. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, everyone. So I'm so excited to again welcome all of you to the AI for Good sub-sessions on AI and biodiversity. We've been bringing together different global experts who really are working at the intersection of how AI can be developed, deployed, and used to benefit and improve biodiversity monitoring and conservation around the world. And today we're super excited to have Professor Lily Xu. Lily is an assistant professor at Columbia University in the Department of Industrial Engineering and Operations Research. Her research develops AI methods across machine learning, optimization, and causal inference for planetary health challenges with a big focus on biodiversity conservation. And Lily aims to enable practitioners to really make effective decisions in the face of limited data, which is so commonly a challenge in these biodiversity spaces, and help them take actions that are robust to uncertainty, that can be effective at scale, and that can be future looking, that can plan for how the world and biodiversity is changing. And she does actually partner closely with NGOs and interdisciplinary researchers to help bridge research and practice to make sure that the things that she builds really have the positive impact that we're all hoping to see throughout AI for Good. So I'll hand it off to Lily, and she'll be talking about AI to help make biodiversity decisions.
Fantastic. Okay. Thank you so much, Sarah. It's really such a pleasure to be here with you and this whole audience. And we are all excited about biodiversity and AI. And what I want to introduce is one idea that we're pitching as the biodiversity decision gap, and think about how AI can help us close this gap. So we talk all the time about gaps in biodiversity. So probably many people, especially coming from like the conservation science or biodiversity policy space, are familiar with this notion of the biodiversity financing gap, which is this over $700 billion deficit, and how much money needs to be allocated on an annual basis in order to reach the global biodiversity framework goals by 2030. So there you can see here the small figure, less than about $150 billion annually, and we have to grow this to over $900 billion annually. So there is a ginormous shortfall in funding for biodiversity. And if we break up the current money that is being attributed towards biodiversity action, we see that there's a large policy gap as well, because all the bars in green here going towards of the sources of money coming in towards biodiversity, coming from things like national budgets and tax policy, existing infrastructure, offsets, financial products, and NGO and philanthropies. All of these, there's some pool of money coming in from each of these sources, but this is drastically overshadowed by harmful subsidies that are reducing or even eliminating and retracting us from these efforts. So the largest source of these subsidies is actually coming from agriculture to feed our industrial scale global food system, which is very necessary to combat kind of present and comparable challenges in food security and reducing global hunger, which is unfortunately still rampant. But the more that we can transition our agricultural food system, for example, from really relying on livestock and kind of large-scale, environmentally destructive global agriculture, the better outcomes you can have for biodiversity. So some of this these gaps need to be coming from policy, where lawmakers are actually first reducing harmful subsidies and then contributing more money and resources for biodiversity action. And relatedly, another one of the gaps comes from resources. So a large-scale study of the world's protected areas have estimated that of the currently existing protected areas, fewer than a core of them have sufficient resources in terms of budget and staffing constraints. And zooming in a little bit more into this number, a Nature Sustainability report found that of all the world's protected areas, they are currently staffed by about 300,000 rangers, but we actually need fivefold of this. We need 1.5 million rangers worldwide in order to adequately conserve biodiversity on the lands that we've already designated. So even though policy has come in and we've come to these international and domestic agreements in order to conserve various parcels of land for biodiversity, we need to actually make sure that they're not just paper parks and only designated by some kind of boundary that's drawn in a map, but also actually has sufficient resources on the ground to make sure that they are protecting the biodiversity that we are hoping to. And another gap that probably many of you are familiar, especially those interested in already working in the space of AI and biodiversity, is a data gap. And this is records from the Global Biodiversity Information Facility. And the top map is looking at the existing data that's collected by these wide repositories of resources. And on the bottom are IUCN species richness maps. So in both maps, blue are the areas that are kind of richer, either in biodiversity records or richer in terms of species. And we can see is that these maps are almost inverses of each other. So the places that we have the most data are inversely correlated with the places that we have the most biodiversity. So there are big gaps in the data as well. But the challenge is, we have all these gaps and there's so much that needs to be brought in across money and policy and resourcing and data to the space. But at the same time, the timeliness and urgency of these actions is very severe. So conservation science is known as a crisis discipline, where we're kind of trying to study a problem that's rapidly changing, that's rapidly declining, and this requires us bring in resources in a very, very urgent way. So in the past 50 years, we've seen an over 73% decline in the average population of vertebrate species. And many of these species are in danger of extinction within our lifetimes. And the World Economic Forum has estimated that $44 trillion, over half the world's GDP, is at risk due to biodiversity loss. And in fact, out of all the global risks to our society, to our economy, this World Economic Forum report, studying over 1,000 global leaders and experts, saw that the global consensus among international leaders is that biodiversity loss is the third highest risk to global development and security. And when these same leaders were asked, when will these risks become a critical threat to the world? The response for biodiversity was 5 to 10 years. So that's how much time we have to act. So in 5 to 10 years, we can't just sit here collecting more data. We can't just sit here waiting for more money to come, waiting for more resources to come. We have to figure out how to make the best use of existing resources as much as possible. So we see this like big urgency and timeliness to this problem. And if we also look at the actions that are currently being driven towards biodiversity and conservation action, we see that much of it is currently positive. So this was a large meta study that appeared in Science last year that looked at over 186 studies, compared various conservation interventions that were done across climate change adaptation, habitat loss reduction, invasive species control, and compared all of these different interventions, imperfect interventions that were making use of data that is imperfect, that had probably a slightly inadequate funding, but it compared all of these interventions against counterfactuals of no actions and found in that over 2/3 of the cases, across these 186 studies, the majority of conservation interventions either improved biodiversity or slowed declines compared to a counterfactual approach. So even with the kind of insufficient resources and data and financing that we currently have, conservation action is making a difference, and it is positive. And what we want to do is think about how we can better guide actions, how we can increase more of it, making better use of our limited resources, and assess which actions are better than others. So, what we see as the global picture of biodiversity is that biodiversity action indeed needs more financing, better policy, and more data. So that all has to be done. But at the same time, today, biodiversity action needs to work within existing funding, existing policy, and the best available data. So what can we do with what we already have? And another way of thinking about this is using this kind of schematic from the very famous Bending the Curve of Biodiversity Loss paper. So this is a very stylized trend line of global biodiversity, historically from when the Living Planet Index was first baselined in 1970s to present day. And indeed, we've seen this large decline, about a 73% drop in many of these species populations. And if we were to continue along this business as usual curve, we would continue seeing these declines. But any actions that we are doing presently to help bend the curve, to help combat these losses, and halt and reverse the state of biodiversity loss, the more we'll be able to bring back up this trend line. So first, there's the financing gap that we've talked about. There's the policy gap that requires stronger institutional and regulatory support for biodiversity. There is the monitoring gap of all the data that additionally needs to be collected and studied and understood about the state of the world's biodiversity. But above that, and in addition to all of this, we have the biodiversity decision gap. So in tandem, all these kind of actions simultaneously, building off of one another, can really contribute to best addressing the biodiversity crisis today. Okay, so that's kind of the state of where biodiversity is and why it's so urgent and important to take action. So let's just understand a little bit better about why action is really hard. So there's many different challenges to taking better action. So first, ecological processes and also social processes, socioeconomic processes, in which are the types of nature-based decisions we have to make are dynamic. So we are working within a changing landscape, and we can't just make a static optimization decision today. We have to recognize that whatever actions we take will change the state of the world, so that we are moving in this kind of evolving setting. And sometimes that could be beneficial because we can leverage positive feedback loops, and sometimes these can be detrimental, in which we have negative feedback loops. There's high levels of uncertainty within the current status of where species are and what these dynamic processes look like. We have very, very large scale, global scale, in fact, orders in which we have to be thinking about designing and implementing these interventions. And we also have to work within these kind of complex socioeconomic frameworks because there are many individual actors who have kind of their own incentives. And even though we might all abstractly care about this idea of protecting and nurturing our world, we all kind of have different priorities for what is most important to us at some time. And what AI is able to do is AI, when designed properly, is able to help us address each one of these challenges to make better decisions. So let's zoom into that. And first, let's talk about what kind of AI we're talking about. So AI means many different things. It's a very overloaded term in which sometimes what people refer to when they talk about AI is, for example, a lot of AI for biodiversity is really focused on how can we apply machine learning tools to better process data. And some of that comes under this purview of predictive learning, like supervised learning, like computer vision to identify animals in camera traps or identify land use change and deforestation. a lot of what AI is referred to now by the media and venture capitalists is really equating AI with generative AI, thinking about large language models and models that are able to create new images. So, sometimes now when people are talking about AI, they're only talking about like chatbots and LLMs. But there's also the suite of other tools under this umbrella term of artificial intelligence that also involve planning and reasoning under uncertainty. And there's also this window, this box to the right of other computational tools that aren't traditionally AI, but very closely related to AI. So these include optimization, causal inference, and statistics. And I want to emphasize as well that machine learning is foundational to many of these. So machine learning is really the process of learning from data. And we learn from data for generative models. We learn from data for supervised predictive models. We learn from data for planning models as well, for example, with reinforcement learning. Okay, so here's like a bit of an overview of all of the different ways that AI can help us like make sense of data and models about the world. And then what about AI for biodiversity? So there's a recent paper of which Sarah is a co-author of the potential for AI to revolutionize conservation. And this is a survey of many different experts at this intersection. I think it's a really fantastic survey to get people familiar with the current state of what tools exist and also what we need to think about in the future. But here's a key figure from this paper that's looking at the different types of approaches and challenges that AI can help address across these three main categories of ecological understanding, identifying threats, and then implementing solutions. And to zoom in under this Venn diagram circle of implementing solutions, this is really where we're thinking about conservation action and designing interventions. And then of everything within this purple circle, there's actually only one that's really focused on like decision-making and designing interventions, which is prioritizing restoration efforts. Whereas the other ones within the circle is systems for monitoring environmental compliance. So that's still really thinking about like, this like data processing, identifying threats, like better understanding the state of the world. Some of these others under the purple box is LLMs for evidence synthesis. And that's really important for us to better understand what kind of solutions already exist and what do we know about each one of these solutions. But it's not really it's not necessarily helping us to decide how to actually implement these interventions. So let's now think about how we can take AI for decision-making and conservation. So the framework we'll be looking at is going from data to decisions. And this pipeline begins with data. So from data, we want to build some model of the world. And this is the suite of monitoring tasks. So some questions we can ask are, under this umbrella of like ecological understanding, such as like, what is the population of a certain species, like killer whales? And this is actually a species that the IUCN Red List has ranked as data deficient. So even though it's like a very large, charismatic, critically important species, we actually just simply don't have enough information on what is their population. And this monitoring task is also trying to understand major threats. So we can understand, where are the biggest threats to deforestation, where are existing threats to human-wildlife conflict. From this model, we want to design some kind of intervention. So here's where our decision-making comes in. And the suite of planning tools can help us answer questions like, determining the set of lands that we should purchase or conserve or restore to help maximize protection for a ecological objective of ours, such as protecting snow leopards. And this also helps us deal with planning if we're budget constrained, so we can incorporate various types of complex constraints. And after we've taken these actions, after we've made some decision, we want to understand how good these decisions were. So that's where evaluation comes in. And we want to understand what was the actual impact of our actions and how well did this help us achieve our goals. So these questions might include, do community managed lands reduce elephant poaching, for example? And again, just like pulling in that, all of the different methodologies under this big suite of AI tools, you can see that many of these tools can map to different parts of this pipeline. So what we'll talk about a lot today is really this like center task of planning, going from some model of the world to determining decisions. And a overall framework that I want to use here are thinking about 4 different types of interventions that we can design with AI. So one is assisting with monitoring tasks. So this is thinking about how to most effectively collect data to better monitor the state of the world and inform decision making. And ideally, what we recognize is that data collection and monitoring is really expensive. It takes time, it takes resources, it takes expertise to both collect and set up the monitoring infrastructure or send people out to conduct surveys. And it also takes a lot of time on the processing side. And AI is making really vast advances in reducing that processing cost. But still, the collection of this data and the processing of it all requires significant resources. So the more strategic we can be about what is the most valuable information that we should be collecting, at what point understanding the threshold on which we have sufficient information is highly valuable. From there, we can think about planning at scale. And again, this is really trying to reach the global scale challenge of what we face for biodiversity interventions. And this includes a suite of tools under optimization frameworks, and then even thinking about dealing with uncertainty and using robust approaches, because we never quite have a perfect model of the environment. So planning at scale can be thinking about how to plan optimally, what is the best decision to make in some kind of static context. But many environmental challenges happen in dynamic settings where, again, the state of the world is changing and it's evolving naturally on its own, but it's also changing and adapting in response to our actions. So our actions are changing the current amount and distribution of species. It's changing the ways that humans are interacting in these landscapes as well. And finally, we want to manage strategic interventions because there are all sorts of self-interested people who have kind of their own priorities for what they want to do and where they want to spend money on and what they want to see happen in our ecosystems, whether it's conversion to agricultural sources or kind of extracting value from existing lands. So we'll talk a little bit about each of these 4 types of interventions, beginning first with optimal monitoring. So from here, I'll be pulling examples from my own work. So I've spent many years working on protected area management and thinking about how can we best reduce threats within existing protected areas from poaching to logging. And there's this consortium called SMART, which is focused on building tools to help protected area managers make better decisions. So they create infrastructure that rangers and other folks in protected areas can use to collect data and monitor and inform the types of actions and interventions that are already being done. And under this umbrella of threat identification, we can look at all the historical data and we can use this to try to predict where threats are. So these are machine learning models that we've developed to predict poaching hotspots within existing protected areas. But what we'll notice is that there are other parks that are on this platform that don't quite have the same richness of historical data. So Rawa Belum State Park in Malaysia, for example, when we were talking to them, we're only just beginning to conduct patrols and to start implementing the SMART system. So at that time, they had very sparse and limited data. They only had 3 months of patrol that looked as such. So much of the park had not been patrolled at all. And we just had no sense of what the threat patterns looked like. So it's just not enough information to pull into a machine learning system. And what this told us to do is we have to think about how we can optimally monitor for threats, recognizing that in parks that are data rich, we can take the existing tools we have for predictive modeling and try to identify threats. But for data scarce parks, we have to think about how to simultaneously conduct patrols to detect poaching activity while also improving the predictive model. So detecting poaching activity means we have to leverage patterns that have already been identified in the limited amount of data that we have. So this is exploiting past patterns, while also exploring areas of high uncertainty so that we can understand more about other areas. So the key idea between managing this exploration-exploitation trade-off is that exploration is really costly. And what we want to understand is, are there ways that we can explore less so that we don't have to, monitor everywhere and collect extensive data everywhere, but we only will monitor and collect data as necessary. And the key idea here is that there's a lot of domain knowledge and problem structure within these ecological and biodiversity contexts that we can leverage. So we recognize that exploration and data collection is really expensive and comes with steep opportunity costs, because any dollar that we spent on monitoring takes away a dollar that we can be spending on intervention design. So what we want to do is integrate ecological insight and domain knowledge as priors into our machine learning models that can both constrain the shape of these models so that we're learning within a smaller class of potential functions. And that just restricts the size of the model space that we have to learn from. And as a result, this guides our model. So we can either enforce hard constraints, things that we know to be true, for example, with ecological insight, or we can leverage existing data that we've seen as priors to kind of impose soft constraints or kind of initial guidance on what we think this model would look like. And some problem structure that we integrated from the protected area management and patrolling context includes decomposable action structure. So we recognize that entire patrol, which is going around a subset of areas and thinking about how good was a specific subset of patrols, can be decomposed into the actions taken within each parcel of land. So it's a very simple additive reward structure where the overall reward, the overall reduction in snares that we are able to achieve, can be broken down into the reduction within each little parcel. But this really reduces our problem complexity from a kind of combinatorial, exponentially large number of actions to much a more feasible linear set of actions that we have to decide on. We can impose various smoothness assumptions. Mathematically, this could look like Lipschitz continuity that just imposes a derivative or bound. Imposes a bound on the derivative or the rate of change of these functions. So here's where we can say that there's similarity across different areas of land. And if we know the poaching levels in one area of land, that gives us information that we can transfer to other areas of land that have similar characteristics as well. And we can also incorporate knowledge like monotonicity, which says that however many resources we put in one area, if we put in more, the potential benefits will only be increasing. So we can know roughly the shape of what some of these rewards are expected to look like. And what I want to emphasize is that it's really a two-way street between algorithmic development and AI, and also this type of use-inspired development by immersing ourselves in these kinds of problems of biodiversity. So when we leverage problem-specific structures and use this to formulate new models for optimal monitoring and exploration, this actually enables us to contribute new mathematical results as well. So by exploring these models that we've identified as relevant to these biodiversity contexts, this can also improve our mathematical understanding of general properties of machine learning algorithms. So next, we'll go from monitoring to thinking about planning within dynamic contexts. And I want to emphasize that a lot of biodiversity decisions really are dynamic. So, we have some state of the world today, and our goal is to design some intervention that takes us to a better state tomorrow. And the things that we might be interested in could be anything from animal density to ecosystem status. And we want to design some intervention that brings us to, higher density of animals, better status, more robust status for our ecosystem. And we can assess our progress towards this in terms of some mathematical objective that we define. So just putting on some terminology to each of these. So we have the state of the world today. Our intervention we describe as an action that we want to take. That brings us to some future state. And then our objective can be described by our reward function. So this whole process is known as a Markov decision process, which is foundational, not just in AI, such as reinforcement learning, but it's also foundational in theoretical ecology, because a lot of ecosystem models of predator-prey interactions, for example, or population growth, are often modeled by ecologists as Markov decision processes. So there's very clear parallels between the kinds of foundational questions that ecologists and conservationists are interested in, and also these AI-based planning tools. And then all the various sorts of AI tools that we looked at can contribute along many aspects of this dynamic planning process. So predictive machine learning and these monitoring tasks help us understand the state of the world. Causal inference can help us assess the impact of our action, and in particular, disentangle the impact of our action from whatever general dynamics are changing within the ecosystem. And reinforcement learning is the suite of tools that help us learn ideal policies for Markov decision processes. And I'll give an example of that in just one second. But there are many challenges that we face across all of this. So for the state of the world, we have incomplete and biased data. So we have to deal with the uncertainty that underlies our models. The actions that we have to take are oftentimes very complex or combinatorial. So I'll give some examples of that. And we also have to do planning over very long time horizons, where the benchmarks that we get of how is the ecosystem improving, and how are our wildlife population changing, and how are human behaviors adapting to our policies. The kind of feedback that we get from that often comes further out in the future. And importantly, all of these challenges are really high stakes, so we want to make sure that we're leveraging as much information we can to move our performance towards something more optimal. So to do planning in these dynamic environments, we want to use tools like reinforcement learning. So one example of this is, again, studying this context of patrol planning in protected areas. So studying data sets from two parks in Uganda, Murchison Falls and Queen Elizabeth National Park, we were able to identify this phenomenon of deterrence, where when rangers patrol one area more, the probability of poaching in the next month goes down, which feels fairly intuitive. So deterrence necessitates sequential planning, because this means the state of the world of where poachers are and how they're behaving actually responds to our actions. But in order to learn a good sequential policy using tools like reinforcement learning, we need to have a good model of the environment. But if we're able to make some estimate of when we patrol a certain amount, poaching goes down by 17%, because our data isn't perfect, and the setting is just inherently very stochastic and noisy, we can never be too confident in any one precise estimate that we make. So even though we might say 17%, we might be much more confident if we are able to relax this number into some uncertainty interval. So if we instead are able to say that this number will fall somewhere between 12% and 23%, that gives us a much more reliable model. So we have to think about robust planning across a whole suite of possible combinations, and that just brings our problem into a much more complex setting, because we're no longer just planning in one environment that is moving and dynamically evolving, but now there's all of these parallel kind of potential models of the environment that are simultaneously evolving as well. So from there, as we think about the additional complexity that can underlay many of these problems, now we have to think about how to best scale up the kinds of planning that we're doing. So conservation interventions oftentimes involve complex constraints. And these complex constraints bring in greater levels of like computational complexity in the tasks that we have to do. So many of these interventions involve physical path constraints. So we might have to stay on roads, or we have to stay on kind of like areas that that our ATVs are able to traverse in, for example. So that creates a routing problem where like the total amount of time or effort that we're able to spend is really limited by the distance that we're able to cover in order to go to various sites of interest. So there's this kind of like really complex path planning problem that involves picking a subset of areas with this constraint of reducing total time spent, for example. We might have scheduling constraints where different people are available at certain times, and then there's a certain amount of time, certain windows of time that various tasks need to be completed as well. So we have to do kind of a mapping between people and task based on these scheduling constraints, for example. Or many kinds of interventions involve very specialized skills, and not everyone is capable of performing all skills. So now we have to do this kind of like matching between subsets of workers who are capable of executing a certain set of tasks with the task with each task that all have differing amounts of time that they might require to be completed. So every single one of these constraints are really complex and involve what's known in AI as an NP-hard combinatorial optimization problem. And what this means basically is just we don't have any efficient algorithms to solve it. So as these problems get like larger and larger, even like on the order of like 1,000 different options, which is very realistic, in thinking of like 1,000 different areas of land or 1,000 different like types of actions that we have to take. So once we get to a certain scale, even like the world's fastest GPUs are unable to solve these types of constraints. So what we want to do is think about how we can leverage like existing tools within optimization to make these constraints more tractable, especially when we're thinking about the dynamic context in which a lot of environmental challenges lay. So what some of my work has thought about is how do we integrate dynamic planning from reinforcement learning and better recognize and work around these kind of like combinatorial or really computationally complex action constraints. And this integrates deep reinforcement learning, so neural networks intended for planning with optimization tools like mixed integer programming. So we can use deep reinforcement learning tools to train estimates of what these rewards can look like. And we can leverage tools to embed these like large neural networks into mathematical programs that we can solve with combinatorial constraints. So we can actually specify whatever routing problem we have or scheduling constraints. And we can make sure that we're exactly matching ourselves to whatever those constraint types are. So it just really widens the types of action constraints that we're able to accommodate. And this is really closely integrating, going from these deep learning approaches, embedding that within these optimization tools from mathematical programming, and then using that in this kind of like iterative approach to go back and forth to both learn what an optimal policy is and be able to execute them on the ground. So the last type of intervention that I want to talk about is involving strategic interactions around self-interested agents. And this takes us to the kind of world of market design and intervention planning, which is really at the intersection of economics and AI. So classical examples for strategic planning include like matching problems of, which Uber drivers should we match with what people, or it's also used in a lot of like public goods contexts, like how to assign patients to kidney donors or assign children to schools. And in the world of conservation, this is used for payments for ecosystem services, which probably many of you are familiar with, thinking about like how much do we have to pay people to do some kind of environmentally positive action, such as conserve or restore various lands. So this is what's underlying the whole world of biodiversity credits and carbon and nature-based carbon credits. And we can also think about how to design auctions to maximize the total amount of like lands from self-interested landowners who are willing to, sell or receive a certain amount of money for taking some actions. In this context, it was to conserve turtle dove habitats by preserving, by fallowing some of the agricultural land, and specifically placing a bit of bird seed for the endangered turtle doves in the UK. So these types of market design questions is challenging for conservation planning because there's many different players who have their own incentives. So in payments for ecosystem services, for example, there are landowners, there's industry and corporations, and there's the people far away, like all of us who benefit or are harmed by conservation protection or pollution. So in conservation, especially, many of the benefits that come from these actions, such as conserving a forest, are positive externalities that aren't captured by any one individual. So no landowner is naturally just paid for not polluting or not cutting down trees. So then the goal of market design is to design desirable behavior and ensure that the system is truthful and efficient, so that the people providing carbon credits or biodiversity credits are actually doing what they promise to do, but also ensuring that the people paying for that, whether it's individuals or corporations trying to reach their like net zero or nature positive objectives, that they actually are kind of getting good value for their money. And I have some upcoming projects related to this space of thinking about how to design more efficient audits for these market-based incentive design systems. Okay, the last bit that I wanted to talk about is looking at this pipeline of going from data to decisions. So we've really focused on the planning task of, from our model, what is the type of decision that we can make? And the last stage really is how good were our actions and how do we evaluate the effectiveness? So the context that I want to talk about here is in Murchison Falls National Park in Uganda, which I alluded to before, where there's very, very vast poaching threats. Ecologists have estimated that it has some of the highest snare density of any protected area in the world. But unfortunately, it has a very limited number of rangers. So there's only 250 people to patrol 5,000 square kilometers of land. This means that there's about 20,000 snares in the park, but only 250 people. So a natural question to ask is just not only like how should rangers be patrolling, but then given the vastness of this problem and how many snares there are, is the small amount that these 250 people are able to do, is that actually efficient? Are they actually providing any benefit between like a small reduction in like the physical number of snares around, because they definitely can't remove 20,000 different snares. But hopefully there's also this kind of indirect benefit of discouraging poachers from coming back in the future. So we're trying to understand how are poachers responding to these patrols. But it's really hard to get at like impact evaluation in these contexts because, as we know, correlation is not causation. And the gold standard for understanding causal effects of the impact of ranger patrols on poaching behavior requires a randomized control trial. But RCTs are very expensive and the opportunity cost is very high. And also in these types of like spatial contexts, there's also a lot of potential contamination. And what that means is if we were to conduct an RCT and randomly pick some areas to be patrolled more, so these are our treated sites, and then we randomly pick some areas to be patrolled less, so these are our control sites. Just by the spatial structure of the park, you'll see that, for example, there are roads that traverse between the park. So it might be infeasible for rangers to go to treated sites and not also go through control sites. So designing these types of experimentations for impact evaluation can be really, really hard in the context that we're interested in. And the second key challenge is imperfect observation. So this is a photo of a snare from Murchison Falls. And even though it's kind of this like head-on shot, you can see it's really hard to find this like tiny small wire snare. So there's a lot of imperfect observation. And for every place that we visit, we know that if we find a snare, then there is a snare. But for every time that we don't find a snare, there's uncertainty in whether or not there actually was poaching in that context. So disentangling this effect of, are we able to detect poaching versus is there actually poaching presence, is a really complex challenge. And what we leverage in this context is machine learning to take the patrol data that we have that is very sparse, very noisy, has like all these kind of like different patterns that change from month to month due to seasonality, and smooth out these like very kind of like noisy snapshots of the current behavior of ranger patrols and poaching in one instance, to develop much more smooth models that look at general patterns of patrol and general patterns of poaching behavior. So instead of just looking at these kind of like noisy fixed snapshots, we can leverage years of historical data to train machine learning models that capture these like typical levels of poaching and patrolling. Ultimately, what we're able to do by integrating machine learning with causal inference is to get at the first result of answering this question of, are poachers responding to ranger patrols, and if so, by how much, to estimate that when rangers patrol a typical area in Murchison Falls, which has about a 21% probability of poaching, if we patrol for an additional kilometer in 1 month, then that probability of poaching will go down by about 45%. So we think that's a very significant reduction in poaching probability, which is notable given that there's only 250 rangers and we're trying to patrol this very, very large park, and there's uncertainty to, what the impact of our actions are. So these types of opportunities to integrate machine learning with impact evaluation to look at the actions that we're taking and figure out, are they actually effective? Do we want to continue doing this? What are the trade-offs? And move towards a world where we're taking better and more informed decisions. So just to summarize, there are many, many opportunities that AI can be applied for decision-making across biodiversity, to think about better monitoring, more efficient planning at scale, and working within dynamic contexts. And overall, I would love to see more work from AI researchers and more partnerships with organizations who are thinking about actually designing and implementing interventions to help close the biodiversity decisions gap. Thank you.
Thank you so much, Lily, for both doing such an eloquent job deciding or describing the deep need that we have to take action for biodiversity conservation, but also, I mean, even talking about the difficulties innate in assessing the impacts of the actions that we take. So I'll kick us off with the first question. And of course, if any of you have questions in the audience, please post them, and then we will also be taking questions from the audience as well. But so one of the questions I wanted to bring up, and you kind of got into this at the end, but one of the challenges I could see facing the adoption of such decision support tools in practice is the difficulty of evaluating not just the impact of actions, but the impact of the use of the tool, right? Because biodiversity conservation practitioners, they're already really spending a lot of time and effort, very carefully trying to make the best decisions they can given the information that they have. So how do you think about when you can't do counterfactuals, right? You can't say like, what if, what if a different decision was taken? Like what truly happened in the landscape? Because you can only make one decision in reality. How do you think about currently in your work or moving forward as we start using AI to try to help us make better decisions in more and more complex environments, moving far beyond the single ranger patrol decision to like these big global policy decisions? How do you assess the impact of use of decision support with AI versus not?
Absolutely. That's a great question, Sarah. And I want to emphasize that the fundamental question that you're asking is how do we evaluate the effectiveness of an intervention? Whether that intervention is an AI-based system or whether it's, like a payment system to incentivize people to, not cut down trees, or if it's some kind of enforcement system where we're, imposing stronger regulations for businesses to reduce pollution, for example. It's very
I guess,
hard.
yeah,
Like
I
the
guess it's that, but also like, how do you know what people would have done without it? Right?
exact
Like, yeah.
yes. So one of the things that we are able to implement if evaluating an AI system is because these are new and because there's a suite of kind of like business as usual policies that are being made anyways, we can, an ideal scenario, create a randomized controlled trial where we actually are having a subset of people kind of taking in this like new, recommendation system versus not. And I think a fantastic example of this that is not specific to an AI intervention, but is thinking about a broad intervention is a paper by Holly Booth that came out in Science Advances earlier this year that was looking at the effectiveness of an market-based solution for paying fishermen in Indonesia to voluntarily release bycatch of endangered sharks and rays. And it's asking, like, if we pay people some amount of money for however much that endangered shark or endangered ray species would have been sold on in the private market, do we actually have better outcomes, or are there kind of, some kind of perverse incentive? Are there unintended consequences of this? What really was the kind of like bang for our buck for this action? And what they found was that largely, like by introducing this new program of paying people for their release, they were able to reduce the amount of fish and sharks and rays that were captured and sold in the market, but actually that there was this kind of unintended consequence of some of the fishermen started just trying to catch more sharks and rays. So it's like this classic example of, well, if we pay people to like not do something, that might create this perverse incentive, also known as the Cobra effect, of incentivizing the thing that we ultimately wanted less of.
Yeah, that
So I
makes
think,
that's such a great example. And it does really emphasize sort of the complexity of the real world. And it doesn't mean that we shouldn't, you know, try to help. It's just I love that, they're kind of really building in assessment from the beginning and thinking quite rigorously about it. But I guess my question is like, was that initial proposal of a potential action generated by experts, or was that generated by AI? And how much are we actually thinking about proposing sets of actions from AI? And how do we assess those differences relative to using, careful evaluation principles to just assess interventions overall?
yeah, I think again, I think from like an abstract level, it is the same. The business as usual in that context was not giving any kind of payments, like not implementing this market-based solution at all.
Yeah.
And then the intervention was adding in this market-based solution. And then when we're thinking about AI to assist with decision making, our business as usual is just, people going from existing knowledge, people like not taking a data-driven approach, people going with more like heuristic or like intuition based reasoning. And the alternative is like giving specific recommendations. So
Yeah.
what ideally I would love to see, for example, is like working across like multiple different protected areas, and then using like more specific interventions in a subset of those that could be driven by AI, and then having others kind of continue as is, and then evaluating the trade-offs
Yeah.
and the efficacy across those groups.
That makes a lot of sense. And I imagine that, as you're building these like deep collaborations with different organizations and scaling, that these types of kind of like rigorous experiments might be possible. But then I guess that also raises the question of like, this comes up with medicine all the time, like the ethics of intervening in only some areas and not others. Like if you think you can help. Anyway, this is a much broader discussion.
Yes.
But I
Absolutely.
do
And
think it's
exactly
like,
like those kinds of like ethical concerns that you mentioned as well is also why we have to find approaches not just to use randomized controlled trials in as many contexts as possible, but also leverage observational data, that data that has already been collected for other purposes, and then try to extract these causal insights from it. And that's exactly what I was trying to present at the very end, looking at this study of deterrence in the context of Murchison Falls. So we weren't implementing an experiment. We weren't doing this kind of like, manipulation of having people do something different for the sake of science, but rather we were leveraging a historical past event that introduced a shock into the environment. And that was actually a historical field test that was done to evaluate the quality of our machine learning predictions of poaching risk back in 2018, and seeing how the differences in patrol behavior during that very fixed 5-month period of time where we were asking them to patrol different areas, that created this kind of exogenous variation that enables us to disentangle potential confounders between areas that they were patrolling more versus patrolling less. And again, there's this close integration of machine learning with insights from statistics and economics to figure out how can we get these, unlock these insights of the value of intervention, of the value of here the intervention being patrolling more or patrolling less, without having to do this potentially unethical manipulation.
Yeah, and I think some of those ideas are probably quite familiar to anyone in the audience who thinks about impact assessment and ecology more broadly, right? Because you can't do this counterfactual. You have to kind of make these space for time assumptions about causality. So I guess the next question I'll ask is, how accessible are these technologies? Like, what's the technological requirements for an organization to be able to use AI for decision support and have them see benefit? What are the requirements, or what are the barriers you see for organizations of different scales to be able to actually benefit from these amazing advances that you and others have been driving in this space?
Yeah. So I think it's like brought one big challenge, big objective of what the SMART consortium that's focused on protected area management is trying to do in general is capacity building and like incentivize, like encouraging and training people in taking a data informed approach, with the goal of not just saying, okay, like let's do management action based on like what we've remembered from like last month or what we feel like might be the case, to actually collecting data and looking at the data and using that to inform future planning. So this whole framework is known as like adaptive management within conservation, and there's a huge push for more like evidence-based planning and evidence-based interventions. So the kind of like first approach is really recognizing like, okay, well, we need to be collecting data. We need to be thinking about the relative trade-offs of one set of actions versus not, and understanding what the benefits and trade-offs are. So I think that first step is building up that capacity building for collecting and understanding data in the first place. And then from there, understanding like at what point is something AI-able versus not. So when is data sufficient? When can we use this? What do the recommendations mean, and where did they come from? Like all of these questions about like understanding what the properties of an AI-based recommendation gives us means also understanding like what is the quality and information of the data that's going into these models. And a lot of that intuition is already being built by current approaches for when people are trying to leverage data processing tools like understanding species distribution models. Like we have to have that kind of like scientific questioning of, is the data available going into these models sufficient for us to extract insights about like, okay, well, if this is where our models is telling us like there's the most richness in biodiversity, but we are using citizen science data, and that data is all coming largely from people in wealthier areas and users in the global north, then we have to recognize that it's probably imperfect. And we have to think about how to counteract that. So I think all of this intuition that is already being built about integrating predictive machine learning methods into the planning approaches is like a a foundational element of it. And what I really want to emphasize is, all the technologies that are available now for data processing at scale, in natural language processing and chatbots, none of these were possible 10 years ago, and none of them were like integrated into biodiversity planning 10 years ago. And I really see like intervention planning and design as like the next cusp of what's happening. Like, yes, like these tools are much more exploratory, but I think that the capacity on the ground, the amount of like real-time data that we're collecting, and also the need for scaling up a lot of these systems is such that 10 more years from now, I think that there'll be a lot more capabilities and adoption.
Yeah, that makes a lot of sense. So maybe like just following up on that and tying in a question from the audience. So Boyang Zhu asked, like, how do you balance sort of specialization and generalization in your research? And I actually think this is probably relevant to that question of adoption, right? Like, how much effort is required to design this system for a specific area, even within SMART, right? Like, if you want to deploy these tools within the SMART network, how much expertise is still required to like specialize it to the context, which is of course a really important dimension in a certain area? And how do you kind of trade off like the methods and the understanding for specializing and building in all that context in a specific area versus trying to understand like what can generalize, or designing tools that are generalizable?
Absolutely. So I like to think of a lot of this like AI development work as use inspired machine learning. So trying to say what is a challenge that practitioners are facing? How does that map to like how do we formulate that as a model? How would we solve that model algorithmically with existing AI and planning tools? But then there's typically a point at which this breaks. There's assumptions that we have to make in what that model looks like, the availability of information, the timescales in which we are able to learn. A lot of that breaks when we are trying to take these tools and systems that were like largely developed for like much more like resource rich and data rich contexts, like in digital context in Silicon Valley. So the translation breaks for some reason, and then that uncovering how do we remedy the thing that broke is the more generalizable, like foundational, like AI advance that needs to be made. And then once that is developed, we have something that's kind of like a much more practical general system. And then the application of that, I think, should initially always be very, very targeted and like closely working with practitioners in a very specialized local context. And then from there, hopefully we can find things that scale up a little bit more. And I also want to emphasize that there's typically a gap between what is practical in the from a theoretical standpoint and like where can we get really nice like mathematical results and kind of new theorems, and oftentimes for that we do have to make more assumptions, and then there's relaxations of those assumptions that we have to make in order to make this practical for real world deployment. But kind of going back and forth between like, okay, let's develop those like foundational advances and then go back and say, okay, let's deploy some variant of the system that works in real life. Oftentimes it's kind of like a back and forth process between something that's like much more generalizable from like general AI for intervention planning that could be applied not just to ecological decision making and biodiversity, but also healthcare and education and public services, to going back and making sure that something actually is practical and useful in a specific context.
Yeah, that really resonates with me. I feel like, in the work that I do, which is like very, very different set of methods, we kind of find the same thing, right? You talk, you really spend a lot of time listening and working with direct practitioners on the ground to identify kind of key shared challenges. You work on addressing those challenges, and then you kind of go back and understand how much that did or did not actually address the challenge. And you're kind of constantly iterating between sort of like zooming out addressing key general barriers and then zooming back in and understanding like how to actually make those relevant and vice versa. And I think this is probably true for many of us who are working in any sort of AI for good space, because there's so much specificity in the problems, but we also find, talking to each other, that there's so much generality in the challenges as well. Amazing.
Yes, and what I really want to emphasize is like a lot of these challenges of like how to like, efficiently allocate resources, how to like make decisions on uncertainty. A lot of these challenges have really been faced in other contexts, like again, education and healthcare and transportation, and like mental health interventions, behavioral interventions. And we just have to find like the appropriate mapping. It kind of has to be like specific in a context, then we abstract it out, and then hopefully that becomes a little bit more translatable. And just as there are, just as we have to like adapt to like a local context when going from one landscape to another, we also have to do adaptation and adoption when moving from one domain, like healthcare, to environment.
Yeah, amazing. Okay. So thank you again, Lily. This has been super informative, and it's such an important dimension of this overall system when we're trying to think about biodiversity preservation. So, I really appreciate you taking the time, and I look forward, all of you can look forward to the next one of these, which will be coming up soon.
Yeah. Thank you for the discussion. Thank you, Sarah. Thank you, everyone.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.